Hi, my name is Tim Farley. I am a principal security consultant with Optiv, and today I'm going to be talking about adversarial testing of smart health card apps. And who I am, I was a software developer for many years. I got into reverse engineering and protocol analysis type things, and that naturally led to internet security type research. So I was recruited to Internet Security Systems, which became part of IBM. And at various times, I've worked for other vendors around the security space. And I have 3 patents with my name on them, and I work in the Atlanta area. So today we're going to talk about the problem of testing or verifying COVID vaccinations and tests at scale, right? What are the computerized solutions for this sort of thing? There have been various non-US solutions, and there is the US North America type solution, which is called Smart Health Cards, which is what we're going to focus on. But a lot of the kind of principles apply to some of the other solutions used in other countries. And we'll talk about what the threat model is, and testing actual apps. What sorts of application tests might this come up in? So what are COVID vaccine credentials? If you're in the US, you've probably seen one of these cards. It's the CDC vaccination record card. Probably a lot of InfoSec professionals saw this card and thought, this doesn't seem very verifiable. There's no printing fanciness on it. It's just a simple black and white card. So, immediately the concept of people forging these things obviously came into play almost immediately. And of course, nobody saw this coming. Of course, people saw this coming. There are fake vaccination cards all over the place, right? People are selling them. People are making them for themselves. So this is a problem. If you're really interested in verifying that people are vaccinated, how do you create a credential that can actually be verified? And let me say that throughout this presentation, the smart health cards that I'm talking about are mainly used for vaccination credentials, but they can also be used for COVID tests and other sorts of credentials. So it equally applies to a COVID negative test. So why do we need a digital way to do vaccine verification? Well, the problem is that you've got situations like large events, you've got airport security, you've got various places where people would like to verify a vaccine credential, and it's time consuming. And, putting people in these types of situations in the role of trying to detect forgeries is, not great. So nobody likes to stand in line. So how can we avoid this possibly with digital technology? So what would the requirements be if you were going to try to solve this problem, right? Well, obviously you'd want something that's cryptographically verifiable. Typically, you're going to need some kind of federated trust authority because you're never going to get a single central agency that's going to have everybody's vaccine credentials stored. For instance, the European Union is a good example. European Union does vaccinations, but each country is in charge of its own vaccinations. So you have to have a way of federating the trust back to the country impossible. You want to be able to verify without the internet, at least in some scenarios, right? So you don't want to have internet. Obviously, for privacy, you want to have a minimal amount of data in the credential, right? You don't want to be passing around people's entire medical history just to verify that they're vaccinated. These credentials typically are going to need to have vaccination, testing, or possibly even recovery status if that's plays a role in your checkout. You know, some countries, if you've recently had COVID, that's as good as having a negative test for entering a facility or something if you've recovered. You want to be able to show this on a smart device screen, you know, show your smartphone. You don't want to have to hand the device over, right? For obvious reasons. Nobody wants to hand over their device to an agent just to check something. And you don't want to have to, you know, you could imagine you could do this with NFCs or BLE. But the problem is not everybody's smartphone. People have older smartphones that don't support that stuff. You want to be able to use technology that everybody has. And then, of course, you want to be able to use a technology-less solution for the person. You want to be able to print something out on paper that you can verify, right? So these are sort of the common denominator of what everybody sort of shot at as they were developing their solutions, right? So outside the US, there were a whole bunch of different solutions, and there still are, and are still being used because COVID credential checking is obviously a lot more common outside the US. Early on, there were a lot of problems because there were some naive solutions that were done where they had things like a hologram in the app or a fancy graphic, an animated graphic or something. And people found very quickly that they could fake that. They could convince the app to display the graphic by manipulating the app, by jailbreaking their phone, et cetera, et cetera. So that went by the wayside very quickly. But of course, everybody was iterating as the COVID pandemic went on, so more solutions came along. But you still see iPhone and Android apps with fairly naive solutions. This is an app that I used recently. I had to do a COVID test. I was negative, but it displayed after I finished the test and went through the procedure with the little smartphone app. It was a home test. It displayed this barcode, and I thought, oh, well, that's fancy. I wonder who can scan this barcode and what's in it. You scan the barcode, and all that's in it is this little piece of JSON, and obviously it doesn't have my identity. It just has like an ID number, which is, you know, who knows what that is, and a date, and it's eminently forgeable. It would be trivial to create this barcode and display it on the screen without actually putting the app up. So that whole idea of a naive implementation where you're supposed to trust the app is still out there, kind of, and you have to watch out for it. Obviously, like I said, there were different solutions in different countries. All of these jurisdictions have their own solutions, which we will not be talking about during this presentation. But I welcome you to try to apply some of the techniques I talk about here to the solutions that were adopted in other countries, because many of them use some of the same design principles. So what did we do in the United States? What we came up with, or a group came up with, is this idea of smart health cards. Now, it has kind of an interesting history of how this came about. Early on in the Biden administration, there was an executive order to try to deal with some issues relating to COVID safety and travel and so on and so forth. And there was a line about producing electronic credentials, right? Well, like everything else, this created a lot of controversy almost immediately. This executive order was in January 2021, and immediately there was controversy about vaccine passports. Are we going to force people to have vaccine passports? Even though if you read the text of the thing, it was all about international travel and trying to make that standardized and easy. Very quickly, the White House said, yeah, we're not going to do that. We're not going to do a vaccine credential. But the problem is that, of course, there are other situations where credentials were needed. People still wanted to solve that problem that I was talking about of, I've got 20,000 people I want to let into this event, and I want to know that they're vaccinated. How can I do that quickly? So as often happens in industry and whatnot in the United States, third parties jumped in. And they had to jump in because of this, which is a huge variance in proof of vaccination policies in the United States, right? Some states explicitly banned any sort of governmental checking of vaccination status. Other states actually implemented their own and had it as part of, for instance, in New York City for a while, if you wanted to go into a restaurant, you had to show some sort of credential, and they have their own app with a digitally verified credential in it that you use to solve that problem. So the national solution, notwithstanding states like New York that implemented their own, was the Smart Health Card. And this came out of a non-governmental organization called the Vaccine Credential Initiative, which was a bunch of nonprofits and so on and so forth that got together and said, hey, what can we build? We need to build it quickly. We need to use existing standards and make it freely available. And then at least if somebody wants to do vaccine credentials and vaccine verification, there'll be a standard that is adopted, right? And it saw a lot of adoption very quickly because it had organizations like MITRE and Boston Children's Hospital behind it. And everybody jumped on. All the major healthcare organizations that have health portals practically jumped onto this and supported it, and now support it in their software, right? So they, of course, they wanted to do it quickly. So what did they do? They used existing standards. It's the way you build something that quickly, right? So they built it on top of all these standards. The verifiable credential is a W3C standard for a generic way of handling credentials. JSON Web Tokens and web signatures and web keys are all things we're familiar with from testing web applications. These have been in use for many years in applications. Another standard that had already been in use, but if you don't work in healthcare, you may not be aware of it, is the, I think it's pronounced FHIR, F-H-I-R, HL7 standard, and basically that's in the standard for encoding health information. So if you want to, encode a record about a treatment or something, and you want it to be accepted by another healthcare system, and they'll understand what you mean in a standard way, it's a way of encoding all that information. So that part was adopted to encode, for instance, what vaccine did this person have and what was the dose and things like that are medically interesting, but maybe not anything that would be handled in a web standard. They use ECDSA signatures, something we've seen a lot of in other applications. They use the Deflate algorithm from Zip, or PK-Zip, wherever you want to call it, but a well-known data compression algorithm that there are a lot of free implementations of. And then they use QR codes, right? If you want to put this thing on paper, you're going to have some sort of a barcode, and QR codes are a standard that you can use fairly freely. So they glued all this stuff together and turned it into what is smart health cards. Now, as is typical for a lot of these standards, there are a whole bunch of GitHub repositories of sample code. And you can get Python code and Node.js code and all sorts of code to implement your thing. But right here, you can see in one of the README files in the development tools. So here you can see it was none of this code is meant to quote unquote robustly validate actual smart health cards. You should use an adversarial threat model, and they leave it up to you, right? You have to figure out the threat model of your own application, which is always true, but it was a little bit disappointing because there are some very obvious threat models to the way these things are used, which we're going to talk about. But you know, it's like you could have at least provided a threat model. So we'll try to, we won't do a full threat model, but we'll talk through what some of the threats are, so you can think about that. So what are these design elements and how did they put them together when they created smart health cards? Well, the verifiable credentials has this basic design that it uses. It basically groups things into three individuals that are involved in any credential. You have your issuer who issues a credential to a holder, which is going to be, you know, an application who has the credential. But in this case, the holder for a smart health card is a person, right? The person whose record it is. And then you have a verifier, somebody that needs to know that that record exists and is valid. And the person will, you know, present that to a verifier, and it can be verified. So that's why you want the cryptography, so the verifier can do what they need to do. But the key to the process is centering the user in the process. They get the credential issued to them, and they're in control of when they present it to another individual. So there's no passing around of people's vaccine credentials behind their back. You decide whether or not you want to tell someone whether or not you're vaccinated. So that was a kind of a fundamental principle of how they designed the whole thing. Of course, a JWT and a JWS, the signature part, these are very familiar to anybody who's tested a web app. You have three elements. They're typically encoded in base 64 and glued together with dots in between them. But before they're encoded, the two first parts, the header and the payload, are just JSON bodies with a few key pieces of information in them. And then the signature is some sort of cryptographic verification that we know where the rest of it came from, right? By virtue of being able to verify the signature with the appropriate key, we know who issued the rest of the payload, and we know that it's valid, okay? It's encoded as base 64. You see these all the time if you're testing a web app. You learn to recognize that lowercase EY, uppercase J, you know, you see that in a blob of base 64 and you know, oh, there's probably a hunk of JSON in there. That might be a JWT. So that's something, you know, one of those things you learn when you're testing web apps. This is exactly what a smart health card looks like when you see it in its digital form. If you see one in a file, they have this little envelope they put around it where it says verifiable credential, but you still see the familiar JWT kind of format. There is a little bit of a difference in the header in a smart health card. It doesn't say JWT because that's not what it's intended to do. It has these three fields in it, right? It will say algorithm ES256. This is a public key cryptography. We'll talk about it in a minute. So we need to know which key we're using, right? In a JWT, typically you use the same key because you're presenting it back to the server that issued it to you and they have the key. In this case, someone different than the issuer is going to have to verify it. So you need to have a private key and a public key. And that's where the key ID comes in. And then Zip Deflate indicates that we've got some compression involved in the format. We'll get to that in a second. The reason for the Zip Deflate is, as you know, JWTs are intended to be very short because you're often going to put them in an HTTP cookie. You're going to transmit them back and forth constantly. You don't want them to be gigantic. So that's why we use little tiny field names like ISS and EXP and NBF. If you like expressive variable names, that's super annoying. But there's a reason for it, which is we want to keep the JWT short. The problem is that FHIR encoding for the medical information that we're going to put in the payload, it happens that it's not super concise, right? It has a way of encoding stuff, and we want to follow it so that we're following the standard, so that existing code can deal with it. But it happens that it's not concise. We do want to keep it concise because we want to put it in a QR code that can fit on a smartphone screen, right? And obviously there's a dot resolution issue on smartphone screens, particularly if you don't have the latest and greatest smartphone. So we don't want to use, a gigantic QR code. We want to use one that has a reasonably large dot size. So just to make sure that this all works out, it uses Zip Deflate compression on the payload in the middle. So if you try to take a smart health card apart using a standard JWT tool, which just unpacks the base 64, you may erroneously reach the conclusion that it's encrypted. It's not encrypted. It's plain text in there, but there is a Zip Deflate step that you have to follow. Once you do, take the deflate compression off, you do see some familiar looking JSON. You have an issuer key up there in blue, and you have a not before timestamp and some of the standard fields. This is a revoke ID, but then all that stuff in the middle you can see uses that fairly verbose FHIR encoding, so that the vaccines are encoded in a very specific way. For instance, that 207 is a code for a particular vaccine type. But as you can see in red, the amount of personal data that's actually encoded in a smart health card, a COVID smart health card, is very small. It just has the patient's given name, legal name, and their birth date. That's it. There's no, no federal ID numbers, no health record numbers, and that's deliberate because you're going to be presenting this in places where you don't want people knowing all your details. You just want to tell them, yes, I'm vaccinated. That's all you're going to find out from me. So there's enough that you can verify with the person's ID who they are, their name and birth date, but that's it. That gets encoded, deflate encrypted, or deflate compressed, and then base 64 encoded in that payload. And just to show you that it is really using very standardized stuff, you can fire up CyberChef and clip the middle part out of a smart health card, and all you got to do is use from base 64 and then raw inflate and then JSON beautify, and boom, you can get the smart health card out of the middle. So it shows you right there that this web-based, JavaScript tool that uses standard data transfer algorithms can do the job, right? So what are those keys, those JSON Web Keys? They look like this. Unlike, you see the standard keys that are usually this giant blob of hex, a JSON Web Key for the ES256 algorithm has a more descriptive format here, where you actually see this is an elliptic curve algorithm, so it consists of consists of a point, an X and a Y, on an elliptic curve. So you've got X and Y, you've got the curve identification and what the algorithm is, and a key ID, right? And these are stored on in a file somewhere where we can pick them up and use them to verify keys. And this is this is a standard. It's used for other things. And here's how that verification happens. If you had a Smart Health card on the left, you've got the 3 parts, header, payload, and signature. You can pull 2 fields, one out of the header, one out of the payload. The key ID tells you what key you're looking for. If you get the issuer field out of the payload, that's going to be a URL. You go to that website, you use TLS 1.2, that's specified in the spec that it has to be 1.2 or above. And then you add /well-known /jwks.json, the standard file name that a lot of folks use for JSON Web Keys. And boom, you should find a set of keys, and you look up the one that has the ID that matches, and you use that to do the crypto to match the signature. And that's how you know that that website vouches for that Smart Health card. Now, some of you who are getting ahead of me may realize, oh, wait a minute. All we know is that that health card matches this website. There could be a problem there. Yeah, there is a problem there. We'll get to that. ECDSA uses a public-private key pair. This is just kind of going over what I just said. The public keys are fetched from a public location. You can have multiple keys. The specification recommends that issuers rotate their keys. There's a way to, remove a compromised key so you can revoke it. There's also a couple different ways to revoke keys, including some optional certificate-based functionality that I have not yet to see anyone actually implementing, but I'm sure somebody does. And then finally, after we've done all that, we can encode the whole thing in a QR code. There is one step that I didn't do a slide on where before it's actually encoded into the QR code, it's made into a URL looking thing, SHC : and a bunch of numbers. The reason for that is a lot of apps expect there to be a URL in a QR code. So that sort of gives them an easy way to say, oh, okay, this URL, goes to the SHC. And they actually registered that prefix for the URL. So if your application wanted to handle it that way, they could. But basically, once you take that SHC URL encoding off, you get right into the formats I've been talking about. Now, QR codes can be from V1 to V40 in terms of size, and that's essentially the number of dots. And there's some ECC data correction in there. So the number of dots is more than the number of actual bits that you're storing. But we use, for Smart Health cards, we use V22, which is around the middle size. Again, it looks like this. And it's designed, again, to be something that just about any smartphone can correctly display. So you wouldn't have to have the latest and greatest phone. But it's an interesting problem because you could create a Smart Health card. You could, try to create a Smart Health card that was a even more gigantic barcode and maybe test the limits of what some of the scanning apps do. So that's one of the threats, and we'll talk about the rest of the threats in a second. All right, so you've got threats that happen at all 3 of the, personas in the solution. At the issuer stage, you can have all sorts of, most issuers are websites, right? I got my Smart Health card for my vaccination off my hospital's website. But if that website had a bug in it, I might be able to steal other people's vaccine credentials. If it was a statewide site, maybe I could find somebody that has the same name as me and use their credential as if I was them. There are a number of ways you can mess up the signature calculation we'll talk about later. The private key could end up getting leaked somehow or stolen, which would allow you to forge credentials from that issuer. The holder, if you are using an application to hold your Smart Health card. There are a number of problems that could happen there. It could not verify it sufficiently. And then if someone is relying on the Upholder app to be valid, which is not a good idea, you should always use a verifier app to verify one of these things. But potentially malformed Smart Health cards, you can always fuzz any sort of data format like this, and maybe cause a crash, that sort of thing. On the verifier side, there's all sorts of issues with trust federation. Remember, I talked about that, where we can't, there's no way we can have a single issuer of all vaccine credentials. So we have to be able to have a way to trust different, and that's how we use those issuer URLs and those key IDs. But who is your trust federation, right? Who do you trust? If are you not verifiers? Are you not verifying them sufficiently, right? Are you just checking the signature and that's it, or are you checking the overall validity of what it is? And again, malformed Smart Health cards could attack the verifier apps. And it's worth pointing out that you can have malicious actors. It's not just people trying to have fake vaccine credentials so they don't have to get vaccinated. You can have issuers being attacked, right? Obviously, people can want to steal stuff, but you could have someone wanting to be a fake issuer, someone who wants to sell fake vaccine credentials, could abuse the issuer side of it. Obviously, the holders are people who want to avoid getting vaccinated or tested, but want to be able to have a credential to show at a checkpoint or at a a venue or something like that. And then even on the verifier side, you would assume someone that's using a verifier is someone who actually is trying to be honest. But there are situations where, like in cities in Canada, many venues were required to check. In New York City for a while, restaurants were required to check vaccines. Suppose the owner of the restaurant didn't really want to do that, but wanted to go through the motions, right? So could they subvert the verifying process so that it looked like they were checking vaccines and getting an okay on the app or whatever it is that they're using, the kiosk, but they've actually subverted it, right? So you can have malicious actors at all three levels. And then I said there would be trust federation issues. Like I said when we were going through the key stuff, verifying a Smart Health card is you're really just checking the signature using a key that was found at the issuer, and the issuer is just a URL, right? So I don't know if that URL actually represents a valid organization. Now, if I'm local to the issuer and I recognize the URL as our local hospital or our local health organization, yeah, great. That helps, but that's not something you can standardize. You can solve it in a number of different ways. For instance, all the Canadian provinces have their own Smart Health apps for these cards, and they most of them use a fixed list of which issuers they're going to trust, and that basically amounts to the other provinces, right? There's an organization, a secondary organization in the related to the Vaccine Credential Initiative called PathCheck, right? And what that is basically they realized they had a trust federation problem in the United States, and they publish a JSON list of issuers on GitHub, and you can go fetch it. There's also an API that says, okay, we've vetted these issuers. We've talked to the people at them. We know that it's actually a hospital. It's actually a healthcare organization. It's actually a testing facility. So if you can do the crypto and verify and get the key from the right place, then we vouch for that organization. The problem is it's not always obvious, what trust federation policies are being used by a given app, right? So this is something that if you're testing an app, you want to explore that. You want to know who does this app trust, and can you subvert the method that they use to verify a rogue issuer. Verify a smart health card that comes from a completely rogue issuing site. One of the ways that you can potentially subvert that process is a problem that happened for real in the Quebec's verifier app. There was an interesting bug where the app, like I said, these apps are intended, to try at least to work in an internet-free situation, right? So they'll, like most applications, they'll cache information so they don't have to fetch it every time. Well, the Quebec app would cache a key that had gone and fetched, and it would cache it against the key ID value, right? And only the key ID value. And it didn't remember which issuer that it got that from. It would say, well, if this key says it's this key ID, that's that key ID, I'll use that key. And it actually is true that the same key ID is used at different issuers for structural reasons about healthcare organizations. Probably not the best thing that they're doing that, but it is true. Well, the problem with this is there was an interesting attack that you could do against it, right? You could create your own rogue issuer domain, issue a fake, create a key on it that you control, and present a smart health card to a verifier. Like if you're going up to enter a restaurant, show them the code, right? Now, if their verifier only trusts certain issuers, which the Canadian apps do, it would reject you. It would say, oh, well, that looks like a smart health card, but we don't trust whoever your hospital is, right? Then you do a little bit of social engineering with the person checking and say, oh, I showed you the wrong one. That was the one my hospital issued, and then they told me to re-download it. And you load a second smart health card that has the correct issuer, but was actually created using your rogue key that has the correct key ID, and show them that. And the verifier app will use the cached key. It will not go and check it against the trusted issuer, and it will use the cached key and let you in. That's a very interesting attack. And this is something that any smart health card verifier should be tested for. If you're caching keys, which is probably a good idea to cache them, or even preload them if you're going to have a trust group. It's not like there's millions of organizations that issue these things. There's a few, like maybe 1,000 organizations at this point, and each one can maybe have a handful of keys, and you saw how big the keys are. They fit on a screen with a pretty big font. So you could cache all the keys you're going to need in your app, and only have to load the ones that are new since your app was last updated. But if you are going to cache it, remember the issuer that you got a key ID from, and only use it against that issuer again. And if you'll avoid that bug. There are a number of attacks against nonces. Nonces are random. I don't want to get into crazy crypto stuff because everybody's eyes tend to glaze over, but there is a random nonce in the ECDSA algorithm for crypto reasons. It's essentially a random number that you put in every time you do an ECDSA calculation, and it verifies that the signature, even for the same data, is going to be a little bit different each time. So it helps against replay attacks and things like that. But the issue is that you shouldn't repeat nonces, and you should use a random value that has sufficient random bits, right? So there are a number of problems with this. Some super naive implementations just used a fixed nonce, just put a random number in there. And if you use a fixed nonce, you can just calculate the private key from the public key if you know what the fixed nonce is. And this is actually the bug that caused the PlayStation 3 code signing key to get leaked in 2010. Even if you are using a random nonce, but you're not randomizing it enough, given enough valid signatures, you can do some fancy math and calculate the private key from the public key. So if you're not doing your nonce correctly, what can happen is people, even without you leaking your private key, people can calculate your private key and then they can impersonate you. So that's a problem for issuers to be very aware of. And here's a problem that came up just a couple months ago. Psychic signatures, brand new CVE. See, it's a 2022 CVE. It was a bug in Java 15 and above where they re-implemented the ECDSA code and they forgot some of the error checks. And one of the error checks is, what if the signature was all zeros? Essentially, if the signature is all zeros, it's not valid. But any, because of the way the math works, an all zero signature, if it was valid, will be accepted for anyone. It's unlikely to affect Smart Health Code smartphone apps, but a server-based app or any kind of app written in Java could potentially have this bug. So it's something that should be tested, psychic signatures. And then there's a number of, this is, kind of goes around to a QA sort of issue and not technically a security issue, but it could be attacked in certain scenarios, I guess. There are kind of some lesser used fields in Smart Health cards. There's an expiration field like there is in JWTs. I have yet to see a Smart Health card that has the expiration set in it other than demo cards. There's a revocation ID field that allows a Smart Health card to be revoked. I haven't seen any that use that. So I think a lot of verifier apps probably do not implement these things correctly. So that means that verifier apps would potentially pass on a Smart Health card that really should be revoked. And then, of course, malformed, fuzzing types of issues I talked about before. What if we violated the V22 QR code rule and created a gigantic QR code? Could we do a buffer overflow of an app? Obviously, buffer overflows is kind of an old school thing, but who knows what people are implementing their applications in. And then, of course, any sort of attack that happens against JWTs potentially could happen against a Smart Health card if somebody was using a standard library and didn't think too hard about some of the lesser used parts of the JWT spec that they really should not be supporting. There's algorithm equals none, which is a way of generating, if you're issuing a JWT and you really don't want to do crypto, but the JWT is being passed around in a scenario where it's not necessary, you can say algorithm equals none. Well, what if you did that in a Smart Health card? Would the verifier just skip the step and say, yes, it's good? There's also a thing, I was not aware of this until I did this research. You can inject a JSON Web Key directly in the header. So you can preload the public key to use in the header. That's got a CVE, right? If somebody used a library that supports that, what would happen if you did that? It would subvert the checking of the issuer. So you could essentially push a key on them that says, oh, yeah, this is the right key. And they would really have no verification that that was the issuer. And then, of course, a completely null signature. Some apps would just pass on that when they really shouldn't. So if you're trying to apply all this, and testing apps for flaws, doing AppSec testing, and you find that there's functionality related to smart health cards in there, how do you proceed, right? There are all sorts of applications that you might be testing that might have this, right? Issuers could be government, public health agency websites, healthcare providers. There's all sorts of smartphone apps that would hold a smart health card, right? And might be attacked using a weirdly formatted one. Verifiers, there are smartphone versions of that, but ticketing and travel systems, corporate human resources applications, there are all sorts of applications that you might be testing that would have smart health card code in them. Here's just a few of the smart health apps that are already out there on the store. A lot of these are issued by organizations. This is one of the Canadian ones. Docket is used by a number of states, but many of these will accept a smart health card. And then, of course, kiosks, right, where people are entering buildings and things like that. People have policies in some areas where they want to check vaccination or test status. And the question is, is the code in the kiosk handling it correctly? And HR business applications. Here's some news stories where various business applications are adding COVID checking stuff. If you're testing smartphone apps, obviously all the normal mobile testing stuff applies, but simple things, don't forget things like permissions, right? Is the app asking for too many permissions? Here's a case where the app is asking for camera permission to scan QR codes. For some reason, it's also asking for microphone permission. I think that's part of the camera permission according to the reason, but it's like, well, does it really need the microphone to scan a QR code? Probably not. If they were a little more careful, maybe they could have done that a different way. But here's, this app is actually asking for your location. Now, if it's a verifier app by a government, then okay, maybe that makes sense, but maybe it doesn't. Interesting thing to look for. And then certificate pinning is an interesting problem that I found at least one app that used an API to pass the smart health card up to a verifier in the cloud, which was an interesting application. This was a verifier app that would typically be used at a, at a checkpoint or something like that. And their cloud API, I think, could handle things other than smart health cards. But the question was it actually doing any kind of certificate pinning, which, often is not a very interesting bug to write in a security report. But remember, I talked about even the verifiers, even the guy at the restaurant who wants to check your your vaccine status. He may want to cheat, right? So he may rig his card, he may rig his device to go through a proxy that can alter the results. And if the app is not certificate pinning its calls to the API, it will not be able to detect that that's happening. And we can alter the response. And here's a case where I actually altered the response to say that it was issued by a fictional hospital. And you can see the UI, when I ran it normally, said partially verified, but we don't recognize this issuer, which is correct. This is a demo card that's issued against a demo issuer. But I could make the app say issuer verified, and I'd be running the real app. You can see the smart logo up there. And certificate pinning would get me around the verification. And this is something that, a typical health code checker probably would not be able to detect why the app was misbehaving. So if you're in the Discord, I'm available to answer questions. I may have already answered some while this was going on. But I hope you enjoyed the presentation, and it'll be interesting to see whether or not this technology gets adopted. Like I said, even if smart health cards don't persist as COVID goes on, other specifications that use similar types of issues could have the exact same types of attacks against them. So the same testing techniques would potentially still apply. And that's my contact information if you want to get in touch with me. So I hope you enjoyed it.